Great. Right, so welcome. This course is mechanics of materials, right? 材料力学, and it will be taught in English, right? Also, this course apply for the cross campus program, all right? So if you are in Yangming campus, you can still using the Teams, Microsoft Teams links to attend this course. And I promise that I won't check the attendance because everything is online. Right, that's it. Okay. So this is sorry. Maybe it's too loud. All right, so I'm sorry for the noise. And I believe I mean, I will try my best to using my poor English. Well, to make it, I will speak English slowly as possible. All right. And if I think that something is really difficult to understand, I will try to translate it. And if I do that, still make you feel difficult to understand my course, there are two ways to overcome this problem. The first one is that you just come here. I mean, after the course, during the break, you can come here, ask me questions. And the second thing is that you can just take a look of my OCW. I have recorded the entire courses in Chinese in the OCW program. So maybe you can using OCW and attend my course in English version. So I believe it can help you to improve your English listening skill, maybe. Okay. And while still understanding what I'm teaching in the content in mechanics of materials. All right, understandable? Yes, good. So let's continue. My name is 年地 Tsou, 鄒年地 Nien-Ti Tsou. All right, and my email is tsoumintn@nycu.edu.tw. Okay. You can see I still using Chinese mind, Mandarin mind to speak my to teach. All right. So my office is 353B. Okay, just above us, engineering building 6. So please please come to see me if you have any question, if you need me. But please email me first, all right, to arrange a time. And remember that if you email to me, please specify your name, ID number, and which course you are attending of my course. I mean, yeah. So sometimes a lot of students want to meet me. I don't know if you didn't show who you are or the purpose, I don't know how to have a arrangement with you. All right. So please to learn how to write the email. Actually, during my 11 teaching years, I have collected a lot of strange email and funny email from students or from my colleagues. So if we have time, I can share with you when you need a joke, okay? When you need a refreshment, if you feel sleepy, I will try to make you feel funny, okay? Humor. Right. So our textbook is geared and would know, right? This is we have many versions, many versions. Um, and also we will have some um, selected practice examples from the textbook. So I encourage you to buy this book. Okay, we have copyright issue, right? So I encourage you to buy this textbook. And when I write down when I select some problems in the textbooks, you may practice them uh, back in your home, okay? And then those those problems practice is worthy because it may appear in quiz 1 and quiz 2, okay? And some extension may appear in midterm and final, all right? So then the grading is class performance 10%, quiz 1 and 2 total 30%, midterm and final total 60%, all right? And one thing I need to mention that class performance 10% is not necessarily give you 10% for all students. It's not possible. Okay. So how can we get the 10%? We have many ways to obtain your bonus in the class performance. The first one is correcting me my mistake when I write down something I made, which is happening a lot. Okay, happen frequently. So if you correct my mistake, I will give you a bonus, and it will increase in your class performance. And I also I may ask you questions if during my class. Okay, during my lecture, I will ask you questions. So please raise your hand and answer the question. And even if you don't answer correctly, maybe you can still maybe if you try your best to answer the question, you can still won your bonus in class performance. But if you never speak out, you never respond in all the way, maybe you may only have the basic score of this class performance. So I don't know. I mean, I haven't designed determined that which score is the basic score. Maybe 6, 7, or 5 or 8. I don't know, depending on the overall performance in this classroom. All right. So don't assume that you will get 10% in class performance. All right. That's it. Another thing is that Nien-Ti Tsou's YouTube channel. Yes, I am going to run myself as a brand, a personal brand in YouTube to start a few days ago. I started thinking maybe I should, uh, you know, because I'm a professor now, I think I'm the full professor, not the associate or assistant. So I think maybe it's time for me to kind of run my own business brand, personal brand. So maybe I will put my uh, insight, teaching insights, research experiences, even advice on admission talks. What does that mean? Which means that if you have a brothers or sister in the high school, they might apply our department. Maybe they can watch my video. Well, I'm going to upload more and more videos. So far, I only have 2 courses list. The first one is last year mechanics of materials, and the second video list is the thermodynamics of solids. Both of them are in English. All right. So yeah. So I'll try my best to upload the videos as many as possible as I can. I can. So please subscribe and share and like it. Maybe yeah. And also, oh, all the courses recording, including now recording, and I will upload on the YouTube. So you can either attend the course in person or you can online lively, or you can just watch the video I upload. Okay. So you have many ways to assess my teaching times, right? Teaching materials. So I'll try my best to offer you the opportunity to obtain all the material resources. Okay, this is the first one. And the second one is that I encourage everyone to join the Facebook club. All right, Facebook club. This is a private Facebook club, and please just apply to join this club, and because all the YouTube and teaching materials will be uploaded there. Yeah, so please join that, and all the announcement and even corrections, they'll all be there. And the next one is AI tutor. The AI tutor is something new, something I'm trying to do. Okay, I'm trying to do is that I create by ChatGPT 4.0 and upload my teaching materials. So this robot is actually answer the questions based on my handouts, my teaching materials. I have tried that before. I have tried this, quite fun. Okay, so for example, if I ask AI tutor, say, what is the moment of inertia? I will teach this. I will guide you to understand moment of inertia later. Okay, later of this semester. So I asked AI tutor, what is the moment of inertia? If I use normal ChatGPT 4.0, it will give me the answer very unrelated. Although it actually answered the moment of inertia. It give me right answer, right definition, but it's not related to mechanics of materials. So if I just so this AI tutor is not the same as the ChatGPT 4.0. It's customized. I also encourage this AI robot answer your question and also giving the PDF file name and page. I encourage it to do that. However, this function is sometimes not work very well. Okay, sometimes not working really well. Doesn't work really well. The page may not write. Maybe it's kind of 1 or 2 pages difference, but maybe you can see the part of that in the PDF. All right. So, oh, by the way, please interact with it any creative way you can think of. Okay, so if you find that it can help you to maybe solve the problems that I selected, you can tell me. And also, if it solved the problem incorrectly, and then please report, which is not surprise because they are not always correct. So don't believe everything the AI robot tell you. All right. So just fun, and you can discuss with it. Okay, discuss with the robot, and if you find that the problem solved by the robot is incorrect, can you make it right? Can you make it right? Okay? Can you teach the robot make the solution right? So if you done this, please report them. Please report what you did, what you done. Report to me. I will give you a bonus. Significant. I mean, I'll give you a really good bonus because it will benefit my teaching for the next year. All right. For example, thermodynamics of solid in the past semester, 4 students give me a really nice report about the AI tutor. Okay, so quite fun. So please join me to do some AI tutor experiment. All right, so that's it. Right, so let's have to kind of get into the real deal, real things, the main content of the mechanics of materials. So far, I guess you can understand my English, right? Right? 可以吗？可以吗？可以哈，讲的还算慢吧？OK 哈，算清楚吧？OK 哈，很好，还是很有自信啊哈，毕竟也得过一些奖项了哈。All right, so let's continue. If you cannot understand my explanation, please welcome to raise your hand. Please just raise your hand and let me know. Please, can you say again? Can you explain this again? Please do that. Okay. Welcome to do that. Okay. So syllabus, chapter 1, tension, compression, and shear. Oh, by the way, I will also share the notes. Previously, in the beginning of the course, it will be with the empathy region in this notes. All right, and then I will write down with you. So I will encourage you to print out, or using your iPad or your phone. It's okay. Follow me with the note. But if you really cannot has the device or print it out, I will share with the PDF with my writing, right, after the course. All right. So again, my principle for this teaching course is that I'm do my best to help you to assess our teaching material as possible as I can do. So notes, recording, and discussion platform. You can all an AI tutor and recording all proposed for you or developed for you. So I hope you can assess all the resources of this material mechanics of materials. Yeah, that's it. 听得懂吗？哦，听得懂吗？好，就是我尽量让所有东西都可以让你们拿到。我会有笔记啊，我会有录影啊，我会有AI 的 tutor 啊。你应该好像可以跟他讲中文，我记得我跟他讲中文，他是会用中文回答你的。OK，所以当然英文他也没问题了。Alright, so let's enter the syllabus. Chapter 1, tension, compression, and shear. Chapter 2, actually loaded members. So basically these two chapters are kind of combined together, okay, because tension and compression, normal, you can see that they are kind of actually loaded in the actual direction, all right? But the shear may related to torsion more, okay? So kind of axial loaded and torsion, and then we entering a really, sorry, I should plug this too. 4 and 5, chapter 4 and 5 are together, all right? 4 is kind of required knowledge for chapter 5. So if you don't know if you cannot understand chapter 4, oh my God, chapter 5 will be completely messed up. All right. So please, when you encounter chapter 4, please understand them entirely, thoroughly. All right. Otherwise, your chapter 5 will be a mess because every problem in chapter 5 will be related to chapter 4. If you cannot solve this, everything in chapter 5 will be, you cannot solve it at all. All right. And chapter 7, analysis of stress and strain, which is really important for material science engineering department students. All right. So this is the most important things. And then chapter 9, I don't think we have time because we only have 16 weeks. Okay, so I don't have time to talk about this. Right. So the mission mission of this course, why we learn this? Because we need to know the materials can be deformed or break or fracture. Okay, so we want to see that if this material safe enough or can do its service usable, is stable. So imagine that you are sitting in a seat, in a chair, okay, in the chair. You need to be safe, right? Or it can be stable. If this is wobbly, it's not good, right? So you can see that this bridge is a system of a lot of materials combined together as a system. So if this system or this material is not good, it's not safe, it will end up look like this, and a lot of people will die in this accident, right? And also, you can see that assume that this is a metal bar. Okay, this is a metal bar. Although this bar is strong, okay, it's really, really powerful, it's strong. But because its shape, if you just press it, the material is okay. But because the shape is too long, it will bend. So, uh, this is not stable, but this is okay, right? It doesn't break. So stability is also an issue in this course. Okay, so what we are going to do is we are going to do a safe design for the materials that we learn. Okay, so this is quite important course. And then our basic assumption is that although a lot of students or your senior previous few years, some of the review comment, okay, review comment for my teaching is that this course is the most difficult course in this department. they say that. Well, but for the mechanics, this is the mechanics of material, right? There are plenty of mechanics after that as the advanced material of mechanics. Sorry, advanced mechanics. So they will be even more difficult. So actually, mechanics of materials is kind of entry level. It's not, it's a beginner. It's a beginner. So we have many basic assumption. So although it is difficult, but well, relatively it is easy for the mechanics family. All right，听得懂吗？虽然呢，虽然曾经有学长姐说这个是超难，是可能的。他说哇，这是材料系里面最难的一门课。我觉得还好啦，不会啦。哦，其他的还更难的，我觉得。Anyway，他是这样讲。然后，其实，在力学的家族里面，后面有很多什么破坏力学、塑性力学、晶体什么什么力学、阿里不达的，那些都超难的。那真的才是真的难，好不好？So objects has some assumption. The assumption make the problem easier. All right. So objects are solid and deformed. When the materials that you encounter in this course, you can assume that it's just a normal material, solid and deformable. It can be change their shape, okay? Change their shape. So they has continuity. You see, everything continues in this boundary, right? So is that continue? This material is continue or not? No, of course not. There has it has a lot of holes in it, pores in it, so it's not continuous. So we are not discussing this. You can imagine that this behavior, deformation behavior, is so complicated compared to this one, right? So we are not discussing this. Easy, not easy. Okay, and uniformity. You see, everything is uniform, the same material throughout. However, do you think this material, or you can say this material are uniform? No, you have air inside this, right? So this is not uniform, but this uniform. Good. So easy, not easy. And isotropic. So which isotropic means that all the direction, the material are the same. So you can using one number of material property to describe this. But in this polycrystal, you can see that every grain has their own orientation. They are not isotropic. So there are many material properties that you need to consider. The direction are all different. So easy, not easy. And of course, this one is not isotropic. You see the pattern of this property. The pattern of these materials are not in the same direction, right? So it's not isotropic. So easy, not easy. And then infinitesimal deformed, which means that very small this shape change. So you can imagine that these things change a little bit after the tension, maybe, or become a little bit smaller for compression. So really small deformation. But for this one, this material has encountered huge deformation. Previously, it looks like this, right? But the deformation looks extremely large. Okay, so we are talking about like 1% deformation. But now this, you can see that it's kind of almost 80% or 100% deformation. So we're not discuss this. We discuss this. So you can see that our mechanics of materials is really simple. Well, with a really big assumption, many assumptions. We exclude. We don't solve these difficult problem. Okay, we don't do that. However, can we solve this? Yes, we could. Yes, we could. Not in this course, but if you join my lab, maybe you can using simulation model or computer to help us to determine the property of these materials. Okay, so you can imagine that we know how to calculate this. So maybe we can know one brand of the properties. So we can tell the computer, okay, you calculate this and you calculate that. And we assign all the material property, and computer can help us to do the complicated calculation. But our human hand cannot calculate that, right? So computer can help us to do complicated material calculations. So that's what I do. That's what our lab do. Okay, so a little bit advertisement. Welcome. Right. So next, mechanics of materials course focus on several four components, four devices, four things that you can see in our daily life. The first one is link. Well, link is something like the bridge. Each component, you can call it link, right? Easy. Shaft. What is shaft? Shaft is that the wheel in your car, right? You have wheels. The shaft is the things that connecting to wheel. All right. So shaft is a bar connecting wheels. Maybe you can think. Maybe you will think, it's a line, kind of line component, and this link is also a line component. Are they the same? They look the same. They look the same. However, why we maybe you will ask why we separate them as the two items? Because link sometimes it's because we are going to talk about actual loading. Remember the chapter 2? Actual loading. Actual loading means that the link is actually compressed or tension along the actual direction. But the shaft is different. Shaft, although it looks the same, it's a line, right? But the wheels at the two ends is kind of rotating it, rotating it. So you can see that although it looks the same, but the loading conditions are different, right? Loading condition, one is twisted by wheel, the other is compressing by the weight. Although it looks the same, but because the force are different. So you can say, this is link, and the other is shaft for the usage application for the human. All right. So you can see that this bar can have the actual force, or actual force, tension or compression. Okay. Or the shear. Well, I will talk about this later. Okay. Yeah. And also the shaft is that going to twist it, the link. So you can imagine that this we call torque. Torque in Chinese, 扭矩, 扭啦. So you can imagine that the wheels kind of distort this bar. Okay, so how can we plot the direction of this rotation using your right hand thumb with that direction? Well, I don't know which one. Okay, so that direction. So you can see that this is rotate with in from the top of the screen to your U and then going back to the screen. Okay. So this direction with the two arrows means that it is the rotation or torque. But just the one arrow means that this is force. All right. So you can here I can just briefly introduce the symbol for the mechanics of materials. All right. And then beam and column. Beam and column, I guess everyone familiar with that because you can see that when you just raise your see up in your ceiling, you see this is beam, okay? 梁啦 beam. The beam support the weight of all the stuff in this floor. Okay, then support that the beam will support the weight. And where is the load goes? Column, right? So every stuff in our floor will support by the beam, and the beam will make the load transfer to the column and to the ground. Okay, so that's how we build the building. Okay, so beam and column. You see, beam and column. So how can we make the beam and column? Maybe we don't have time for column, but you can see that how we design it, safety design, right? So that's the mechanics of materials taught us, okay, teach us 4 components for human daily life, okay? So now let's enter the chapter 1, tension, compression, and shear. You may find the content in this chapter is really similar to introduction of material science engineering, 材料科学导论. Okay, so I may go through this a little bit, well, I don't know, faster or not. But okay, again, the purpose of the mechanics of materials is that we are going to do a safe design, all right? So we are talking about the stress, strain, displacement, 3 stuff, okay? 3 stuff. And this is component. And when a lot of components combine together, you have the structure, or you can say system. And when the system or component under some loads, under some weight, under some torsion, shear, anything, it might failure. It might failure. So we don't want it happen. Okay, we don't want this happen. So we need to determine, solve the material's limit. We need to say, this material cannot bear, cannot suffer the load exceed 50 kilograms, something like that. Okay, so we need to talk about we need to determine that. All right, so that's it. Let's continue. But before we really get into that, excuse me, we need to review a little bit about the statistics. Statics. I believe you learned that in our senior high school. Maybe we didn't say statics, we call that physics. But I believe you heard the term of work or load balance, force balance, moment balance, right? So this is what we are doing here. So just like we did that in the previous few slides, I introduced the arrows, right? So I also want to give you the symbol definition in this course. So please follow the rules, okay? So we can share this as a common language in this course, okay? So resultant force, dashed arrow. So resultant force, what does that mean? Before I go into the resultant force, I will firstly give you the definition for distributed load. Okay, what is distributed load? Which is okay. I'm sorry that this is the first class, so I haven't provided the the handout with the blank. Okay, so I'm sorry that maybe you cannot directly get this empty notes. Maybe 2 minutes later during the break, I will try my best to upload this. Okay, share the links with you. All right. So on the E3. Okay. I'm sorry that I didn't think enough to plan enough to. Okay, I'm sorry that, but right. So what is a distributed load? Distributed load means that this is a load that not concentrate at one point. Not. It's a it's a load spread out spread out through the length. Okay, so here Q1 is the magnitude of the height, the distribution load, and there will be a length of the distributed load. So you can see that the distributed load Q1 here, it has a unit Newton per meter. So which means that this is not load. This is the load per meter, per length. Okay? And you can see that they have the resultant force as a dash arrow. And I will explain this in the next, after the 10 minutes. All right, so that's it. I will give you a break and then see you later. Thank you. If you have any questions, just come to me and I'm going to share the link of my notes.
哦，对，那还有这个地方以后不行，他的又多写字，人家是不想怎么怎么样。应该是一方面，你知道，就是因为中间，他叫什么？中国跟欧洲，在跟你我先这边开始马铁斯，不是马铁斯，这个开始，就这个然后一起啊，那个关键这是我们。哦，就是里面的东西，其实我自己看我的学历和写的里面写，那我感觉才是比较大的，就是因为对感觉，那我说但是比较准，这个主播，做出来的就是这个执行的电子，还有今天晚上的。显示器，为什么不可能？今天哦，你那才进来对哦，那就那个啊，那怎么？什么？哦，我自己，哦，什么意思？养老钱，好吧？是用词，不是，并不了解。哦，对，老师，老师，不是去。是的，就是那个对啊，对的，然后他自己讲，那是考试啊，考试，考试是小考试那个就是这个有什么情况？因为没错，大家没错，所以实际上来，然后小的学，再去，这蛮多的。用的是啊，那我要去什么什么？就是要我说可以的事情，其实这种非常类似，那样我就好这件事。但是我的认识，按照哦，还是我要看。关不到在那里，当然是就是一分钟，是这有不可能，我就是正确。哦，就是在你他如果没是那个，有些东西是可以的。但是这个思路就有的时候，那他就是比如说一个事情，大概在搞，这个资源，按这个上面东西，但是应该是思路的，为什么要做？你知道这个这样就全部这个是应该有，应该没有的，对是。是，但是我自己的去过，那是好像是我去过，我说就是很大时间的样子。 在这个真起步的三个信息当中，你得知道这个真起这种起步的距离，可以这样这就是一个有新的人觉得是，
Okay, welcome back. I just upload all the now notes to the and shared by the Google Drive, and then I share the links in E3 on E3. All right, so maybe you can download it right through your phone or your iPad. All right, so I hope I can help you. This can help you to understand the course more easily. All right. So I just in the past hour, in the last hour, I talked about that the purpose of the mechanics of materials, and then I also introduced 4 members, right? Link, shaft, column, and beam. And also we talk about the assumption of this course. And although they sound difficult, but actually this is actually an entry level for the advanced mechanics families, right? And we also introduced the symbol, right? The arrow means force, right? And 2 arrow means that the rotation or torque by using your right hand rules, right? So now we're entering the chapter 1, and we need to review the statics you learned in your senior high school. Of course, that the name may not be statics, maybe called physics or force balance or moment of balance or something like that. So yeah, you know that the force has direction. So we typically using arrows to do that. So in this random component or random material looks like that, look like a L shape. They have it has a point B, right? And if there is a force acting on the force B, FB, okay, this the subscript is B, means that it acting on the point B, all right? So the F, of course, is called force at point B. So you can say this force is actually what you learned in your senior high school, right? And you can say this is concentrated load. Concentrated load, 集中载重, because it concentrated at the point, right? And this is actually what you learned in your senior high school. Yes, senior high school. Yes. So FE is force B. And then we talk about the resultant force. What does that mean? Which means that actually resultant force is that a lot of force or distributed load summoned not together to be one resultant force. It's kind of a simplification. You make it simpler. Okay, so distributed load, actually it looks like it is a load that divided by the meter divided by length. So this is not, Q1 is not the force. It's the force divided by M, divided by meter, divided by length. Okay, so it needs to times length to become a force, Newton in the unit. So you can see that this dotted arrow is resultant force of this distributed load Q1. Okay. So the FQ2 is a resultant, is a simplified or effective 等效, okay, effective force. So the value is FQ2 equal to Q1 times L. Okay. So when you do the work balance of this system, you shouldn't use FQ2 and then you consider Q1 again. No. You shouldn't do that because FQ2 is a result. It's a resultant force of the Q1. So these two are the same thing. Okay, you shouldn't double concern it. You shouldn't double considering it. Okay, so FQ2 is actually the result of the Q1. Okay, so please be careful about this. Next, let's talk about, sorry, it overlapped with the page number. It is AY. Okay, so then let's talk about the reaction force. Reaction force is 反作用力, 反力, okay? And it has a very special symbol. You can see that. Arrow with a slash. Arrow with a slash, which means that reaction force. Okay, what is reaction force? Which means that that's force due to because of the force you apply. If the force you apply are zero, there will be no reaction force. So this reaction force, all because of the load you applied, you need to have a balanced system. So if there's 0, 0, of course this is 0. All right, and the direction also considered by the load you applied on it. Okay, because if you apply opposite direction, your reaction force will be another direction, of course. Okay, so reaction force. And where is the reaction force occur? Where? Typically, all the reaction force occurred at the place that you fixed. If something fixed your material, that place has reaction force. Okay, for example, this is a link, right? This is a material, and if I apply a force, do you think, ignore my right hand, okay? So this is just, you can imagine this is a floating on the universe, all right? So ignore this. So if this is a force you put here, this is not fixed, so there's no reaction force. So this is not in work force balance, right? So it's moving. But in material science, sorry, mechanics of material, every material is in equilibrium state, in stable state. So you need to have another, if you fixed here, if you put the force, where is the reaction force occur? Here, right? So reaction force comes from something you fix the materials. All right, So you can see that there's a little dot here, little circle here, which means that it's a pin. It's a pin just knock in the pin into the wall, so it fixed that. So it cannot move. It cannot be moved. Okay, if it cannot be moved, which means that it fixed. It fixed means that they has a reaction force. But you see, this link is fixed by my right hand. But if I don't do any force on that, the reaction force is zero. Well, ignore the gravity. Okay, so you can imagine that the reaction force is actually it can be solved by your applied load. 你施加的力可以帮助你去算这些反作用力。Okay. Another thing is that remember the rotation. We call torsion torque, or you can say moment. Basically, it's just rotation. So force with the force arm, right? So it can rotate. So when you see a curved arrow like this, it means more moment. It's a moment, rotation. So you see MA. So the M means moment. A subscript A means at that point. So you can imagine that this point has maybe has a bar to make it rotate. Okay. So that's it. So you see the symbol distributed load looks like this, and notice that their unit is M divided by M. And the force, of course, is Newton. The unit is Newton. I don't need to explain, right? So N, M, and M, of course, is the unit. Okay, I can. So the moment unit is N times M. Okay. Okay. M times N. Force unit Newton. Because it's too easy, I forgot to write it even in the last year. I have another iPad, very old iPad. You can see how thick of this, right? It's really old, but it's still good to make it to have my script. I can just follow what I did and then give the most fluent, most smooth lecture speech for you. So you can see that I brought many stuffs here, connecting. Okay. No question though. I guess this is quite simple. So let's continue. Maybe you need time. All right. So I hope you can follow me, right? Because I take a really slow step. I hope that my teaching style fits you and to let you get used to my teaching style. All right. Go. Now, no more stress. No more stress. Oh, maybe you think why my first lecture I was just spend teach entire 2 hours because we only have 16 weeks. Okay, if we have 18 weeks or more than 20 weeks, I will take my pace even more slowly, and then I may just give the introduction and then I will let you go in the first day. But because we only have 16 weeks, so I'm sorry, I need to make every hour counts. All right. Now, normal stress, really important definition. Normal stress means that normal is vertical, all right? Vertical stress. Stress in Chinese, 应力, sorry. Normal, 垂直应力. Okay? Why it called normal stress? Normal stress means that it will acting on a plan, acting on an area, all right? So you can imagine that really simple definition. If you have a prismatic bar, long prismatic bar, and it subjected to a load P, okay? And then I'm going to give you a prismatic. What does prismatic means? Which means that equal area throughout the object, okay? So you can see the equal cross-section area. If this bar looks like this, it is not prismatic, okay? So a prismatic bar, we are going to make it simple, okay? Make it simple. So prismatic bar, and we'll discuss non-prismatic bar later, all right? So let's take a look. If you have a force, make it longer. Imagine that you can make it longer. And then we are going to see, we cut them. We just see this section, okay? We just see this section. This load's still there, okay? We just see, observe this section imaginarily, okay, in your head. And then we pick up L length, okay? The segment of the bar before loading, and which is L. But after the P, it should looks like L plus delta. Delta. Before the loading, which is L, but after the load, L plus delta. Okay, so you can imagine that it's longer a little bit, P and P. Maybe you think, you only write one arrow. Why you write two arrows here? Because let's imagine that if we cut this imaginarily, okay? If we cut this, you see this, or you see this, all right? You see this? I will ask you a question. Do you think this segment will fly away? No, they stay at the same place, right? So if you have one P here, if you only have one P here, will it stay? No, it will fly away. It will fly away. So if you cut this and you know that this segment is still there, which means that if you are sure there's a force here, right? But you are not so sure if there's a force here. So you can imagine that this bar won't fly away from the right, to the right. So you know that there must be another force to balance it, right? So 2P here. And this 2P here make the L become L plus delta. The delta, of course, is displacement, okay, displacement. And then we're going to say that we take a cross-section, M, the cross-section, just an area, okay, in the middle. You can imagine that this force is actually, sorry, I should put this. You can think of that this is actually a uniform load. uniformly distributed in that area, and the resultant force is P. Resultant force is P. So you can imagine that this resultant force is uniformly distributed at the surface, at this area, sorry, not surface, area. Okay? So the definition of the normal stress of this material at this location, this cross-section is sigma equal to P divided by A. The A is the cross-section area at this position. So units, of course, is force divided by area. So Newton divided by m squared. Okay. I should say this is a sigma, right? Sigma. If you played Mega Man X, you know sigma, right? Well, it's a symbol. I don't know if you played Mega Man X, really old IP. Anyway, I quite like to play Mega Man X, but I'm really poor. I'm really bad in the controlling the things. I just enjoy it. I always make the difficult level to the lowest, and so I can enjoy the game or enjoy the screen. Anyway, so sigma equal to P divided by A. Sigma is normal stress. Okay, normal stress. And we will give you a convention. It's a rule. Okay, the rule. Don't ask why. Okay, just everyone agree with that. All right. So tensile stress is positive. Compressive is negative. Don't ask me why. Everyone believe in this. Okay, remember this. Okay, you see that uniform stress is assumed. So this one can, you can see that we assume the load P here can uniformly distribute it in this throughout the bar. Okay, so you can see that the force P need to be applied at the centroid of the cross-section. So if your force is actually acting on here, oh no, this distributed load is not uniform at all. It may have some, something like that. And then you cannot use this you cannot use this equation for the stress for the entire bar. No. The stress of the bar, if your load is not at the centroid. Okay? So everything is simple here. So you can see that everything is in a really simple, with simple assumption that everything is uniform and the force is at the center, and that's it. So sigma equal to P divided by A. Okay, I will give you maybe you will ask why we need to pick up the segment at the bar, in the bar. Why just saying, this bar P divided by A, that's it. Why? Because I'm going to give you a simulation result. This is a finite element simulation result. All right. What is finite element? You can imagine that mechanics of material we calculate is something like a square or a cube. okay, and the force, and then we determine by our hand. We determine the stress by our hand. It's okay, easy. You can determine by your hand. But if you have a really complicated material or system, how can you do that? How can you calculate by hand? It's okay. Computer can help us. Okay, so we cut all this material into many small elements, small elements. So you can see that there are many shape, mesh, network on this material. So the computer can calculate every single element, what is the stress on it, and then sum it up together and show you. Okay, so this is the power of simulation or computational mechanics. So fundamental simulation. So the bar, prismatic bar here, right? So you have, if you have a concentrated force, and we calculate that, we found that actually, oh, by the way, the blue part. So this is actually, the blue part is the lowest stress, and yellow is greater, and even red is the greatest value. You see the the red value is the greatest value, stress. So you can see that in that bar, the stress value are not constant in all the materials. Actually, the stress is localized. You can see what does localized mean? Which means that every place has different stress value. Okay, so the reason why we use the definition that the P divided by A is that we need to cut the bar and see the real uniform segment, and then we can say P divided by A, right? So that's the reason. And then if we come closely into the real world, not in the mechanics of material world, mechanics material world in this course is kind of entry level, beginner. Okay, if we make us more advanced, more reality. Actually, this this is actually if I make it exaggerate, 夸张, okay? If you have a concentrated force, P, actually, this is the highest stress, okay? You can imagine a stress. Stress is some sort of, you can imagine that by squeezing your skin, all right? Why you using your finger to do like this? You are not hurt at all. But if you're using your point nail, you will feel pain because you have higher stress. Okay, so you see, the concentrated force will occur in a really high stress at that point. Okay, so when we are going to define the P divided by A, you better choose a simpler section. And how does this go? How does the force flow in the bar? You can see that it's just like a water. Okay, the water is kind of flow through the bar. So you can see that that's the reason why this section is, in the middle sections are uniformly light blue. Okay, And the dark blue means that no force at all. So actually, this dark blue place is stress free, which means that sigma x equal to 0. Oh, actually, this is kind of supplement material, 补充教材. Okay, I just want you to know the real world looks like. So when you have a point node P acting on the surface, okay, so you can see that this is a highest point of the stress. But because of the flow of the force, there's nothing. So this place, feel nothing, okay? Feel nothing. Because the force is not acting on it. But because of the flow, the force of flowing, so you can see that, oh, this force are kind of uniform. So it can make it sigma equal to P divided by A. Okay? So when you say sigma equal to P divided by A, the P here, right? The P is the load you act. So yeah, sigma equal to P divided by A here, but may not be here. They are very complicated and only can be obtained by simulation model, right? And then if I introduce this in this way, I hope you can understand why this force cannot acting not at the centroid, because the flow is kind of, it's not uniform, not symmetry at all. So we are not considering this. All right, we're not considering this. I hope you can understand what I'm talking about, right? So definition of the normal stress has been done. And then next, we're going to introduce normal strain. Normal strain, again, a prismatic bar, and we need to give the segment, and the segment has, before the load is L, after the force applied, P E become L plus delta. The delta is displacement. So the epsilon displacement, epsilon is called epsilon. And this called delta. Okay, divided by L. So the displacement divided by the original shape, original length equal to epsilon. So you can imagine that this is kind of a ratio of the deformation. Okay, maybe you can say percentage. Okay, 就有点像是延长率、伸长率，或者是缩短率。Okay, so which means that no unit, because it's rate, it's a ratio. Okay, no unit. This is so important. So you can say percent. Okay, you can say, so for example, 0.02, the strain is 0.02, and you can also say 2% strain. Okay, but keep in mind, 1% strain is really big. It's really big. Okay, 2% is even bigger. All right, so just keep in mind, normal materials strain is under 1%. Okay, so if you create the material, well, it can has elastic strain like 20%. It's not gonna happen. Or you can win Nobel Prize. Okay, sign convention again, tensile strength plus positive, compression minus. Assume homogeneous, of course, the material is the same everywhere in the bar. Prismatic, the material is homogeneous. Yes, this is our assumption, right? So I guess this relatively understandable compared to stress, right? So the next example is really simple. If we have a bar and the bar is the P, and we typically use MKS unit system, okay? Meter, kilogram, second. Given that E equal to 27 km kilonewton, okay? K means 300, sorry, 1,000, okay? Diameter of the bar D equal to 50 millimeter, equal to 0.05 meter. MKS. So typically we will transfer 50 millimeter to 0.05 meter. Okay, this is how M for. Okay, please determine the stress. Easy. Sigma equal to P divided by A. So P divided by pi d squared divided by 4. Of course, this is a circular area. So 27 times 1,000 Newton divided by pi 0.05 divided by square divided by 4 equal to 13.8 times 10 to 6 pa equal to 13 AM pa. Okay, 13.8 times 10 to 6. Wow, that's big. So you can imagine that your stress is typically M pa, okay, 10 to 6. So if you have material and you calculate your stress is 13.8 times 10 to 2 pa, maybe something wrong for your unit, okay? Next, the bar has original length L equal to 2.0 m. When it's subjected to a load in tension, it might elongate, become longer by 1.4 mm. Determine the strength. Well, easy, very easy. Divide by L, 1.4 millimeter divided by 2.0 and 0.0007 equal to 0.07%. So your strength looks like this. Okay, easy, right? Well, later it might be really difficult. Later, all right, later. Enjoy this moment. Simple. You know, when you talk in English and in Mandarin, for my personal experience, I feel I'm a different person. When I speak English, I become more gentleman. I feel more polite. If I speak Mandarin, my ugly part of my heart will appear, will show you. Yeah. So because when I learn my English in the UK, England, right? They 007, right? So they kind of try to make it England British gentleman, right? And when I learned that, I need to I mean, those people, those kind of gentlemen teach me to do that. So teach me how to speak English like them. So my brain structure automatically become then they're so I become more polite. But if I speak Mandarin, I feel safe, become comfortable, and then yeah, ugly part will show. So maybe next time if you have your, your partner, girlfriend, or boyfriend, maybe you can suggest that. How about let's argue in English? And then maybe you will be happy after forever because you're all polite and you cannot communicate well, and then forget it. So maybe you can try that. All right. So next, you have a tube. Tube is a tube like this. All right. So which means that they have two diameter. One is bigger, one is smaller. So it's a tube. 管子. All right. And it has a what's that? Blue cap on it. And the glass, maybe it's a glass, I don't know, but you have the pressure, load on the middle center of the blue material. But interestingly, we are not calculating material blue. We're calculating the stress for material gray. All right. So not this, not blue. Okay. The blue is just a cap. Sorry, the cap that pushing that evenly. So because of that cap, thanks to that cap, we have a uniform force on the cross-section area of that tube. All right. So the sum lambda are P. Okay. And so you can think the P is 240 km, outer diameter D2 130, D1 is 90, and length is 1, and shorten the length delta is minus 0.05 because it's shorter. Okay, 0.55. Okay, find compressive stress. Good, let's go. 1 A pi D22 minus D12 equal to pi 4 130 to minus 90 square 9612 millimeter square, or you can change to 6912 times 10 to minus 6 meter square. All right, so this A, we've done that. The small rounding area, sigma P divided by A, 24000 divided by 6912 times 10 to minus 6 m square. And don't forget that, well, this is compressive, so give you the minus sign here, and equal to minus 34.7 m pop. Okay, so this is the first one. The second one is strain epsilon. Epsilon equal to delta divided by L, 0.55 divided by 1000 minus. So, which means that minus 5.5 times 10 to minus 4. Okay, done. Easy. The next one is more difficult and also has some nice conception. Concept. Next problem has good concept for you. I hope I can finish that in time within 7 minutes. The next concept actually I introduced in the previous few pages, but maybe which is not that thorough, systematic. I can tell you in the next example, right? Okay. Next one is quite important. Go. This is a bar handling a weight. The weight is W. Okay. The steel rod is circular, length L, diameter D, bucket weight W. All right. So find sigma mix. Sigma mix. Oh, which means that the sigma is changing throughout the bar. Okay, not sigma equal to P divided by A, then everywhere has the same value. So please remember that sigma or stress is not fixed, not constant throughout the material. Okay, account the weight of the rod itself, rod density, gamma. Oh, so which means that, can you give me a, tell me, where is the sigma mix occurred? This plan at this point, or that 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 point. Which one? Which one has this maxima sigma max? Give me an answer, and I will give you a bonus. Which place? I mean, I'll give you A, B, C, D, E. 5 points. Which place? Give me your answer and reason. Which one? Sorry? A. Why? Why? Exactly. Very nice. Very nice. Good, 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 good. So what's your number? 39. By the way, this is a really fun part. When you are going to read your numbers, ID number in English, this is difficult. Can you? Difficult. Then imagine 1116. Oh, you are good. 3039. Is that correct? Very good. Prepare reading your number. Okay, this is fun. Anyway, I will talk about the how I prepare English telephone speech. I mean, communication when I'm in UK or US. Anyway, so I don't think I have time to finish the problem, but I will give you the concept. So you see, this is the sigma max, where the sigma max occurred, right? Because it needs to bear the bar weight itself, also the bucket weight. But in this point, it doesn't need to bear the bar weight. You only need to take the W weight. Okay, so you can imagine that the stress is decreasing. Well, it should be decreasing. It is not a triangle, it's a kind of a trapezoid shape, right? Okay, then I'm going to give you a most important concept here. How can we determine the sigma max? We need to cut it. Okay, this is really, really important. If we want to see the sigma stress or force anywhere of the bar, we just need to cut it. I want to see this point, I just cut it, all right? I cut it this place. And then separate it. Sorry, I enlarged the bar, okay? I cut it. I cut it. All right, I cut it. Now, you have a force W here, and you have a self-weight here, right? Okay, you cut it, but as I mentioned, do you think this part will fly away? If there's all this force, they will fly down, right? No, which means that there must be a force in this area to prevent them fly down, right? So this is F mix. This is the most important concept for today, all right? So if you don't understand what I'm talking about, please come to here and I will finish this course today. Thank you.